When we're trying to think about all the different equations on the equation sheet, the first thing to maybe think about is just the rate law, which is really the key central concept in chemical kinetics, because that's going to describe how the reaction rate depends on any of the different reaction conditions. So we introduced the general rate law, where that's thinking about a generic reaction, something like A moles of A react with B moles of B to make products. In that case, the rate law describes this entire equation. So the rate law is rate on the left-hand side. That's the rate of the overall reaction in molar per second is equal to K, the rate constant. That one we don't know the units unless we know the order. So the unit there depends on our overall order. X and Y are these exponents. Those are the orders in each reactant. So X is the order in A, Y is the order in B. The overall order is X plus Y, just adding up the two individual orders. Now, every single one of our equations fits into some piece of that rate law. Just to highlight that with an example, let's say we're looking at the decomposition of hydrogen peroxide. We have an equation. Then in this case, the specific rate law would be something like rate is equal to K H2O2 to some unknown power X. And then in this case, when we're doing different experiments here, what we're trying to find is K, the rate constant. And really, before we get K, we need to figure out the order. The order is always the hardest thing to determine and is what, our given experimental information, either from method of initial rates or the integrated rate laws, the different plots, is going to be oriented around obtaining. So if we start with this example, now when we look at all the equations on the equation sheet, what's going on there? So none of these equations directly have rate in it because we always write the rate law down ourselves. But again, we can see that all these equations are related to the overall rate of the reaction in some way. The first thing in there is the rate constant K. So again, that's something that has units that depend on the order. We can't write its units, but it does have some units. Now, the first thing maybe to think about is how K depends on temperature and activation energy. That was the first equation that we looked at, and that was all these versions of the Arrhenius equation. And what that's going to do is describe, again, what it said, how K depends on activation energy and temperature. So all those maybe I'll highlight in yellow here. So the Arrhenius equation is all of these yellow equations. So note that since this is the case where we're thinking about temperature and activation energy, these equations all have these certain variables. So they all have EA. The Arrhenius equation introduces these variables. So EA is activation energy. The unit there, normal SI unit, would be like joules per mole. That will match if we look at the next unit there, R. So R, remember, is the ideal gas constant. So that's here given in joules per mole. Now T is temperature in Kelvin. Since that's in Kelvin, we need to be able to convert that to or from Celsius. So that's the unit conversion that's shown there. The pre-exponential factor, that's another one where the units depend. It always has the same units as K, because one thing you should remember in this part of the class is that any special function is completely unitless. So e to some power always comes out as a unitless number. The same thing with ln of something. So ln of A or ln of A naught, all those are all unitless numbers once you take the natural log or e to the power of. These other forms of the Arrhenius equation are shown here. So we also have this form here. This is sort of a 2-point form. That's useful if you want to go from just two temperatures. This, you'll notice, doesn't have the pre-exponential factor A in it. So that's the nice part about this version of the equation, is that if I just know the rate constants and the temperatures at 2 points, I can solve for the activation energy. The other form that we're going to use is this one. This is the one that we're going to use to make the linear plot, because this thing looks like the equation of a line. So if I look at that, and I make a line that has y is equal to mx plus b, if I plot 1 over t on the x-axis and ln of k on the y-axis, I'll get a line that has a slope of negative e over r and a y-intercept of ln of a. So this is what we want to plot to determine the activation energy from a plot. So all three of these equations and these constants all have to do with how the rate constant K depends on temperature or depends on a catalyst, since a catalyst affects the activation energy. It also probably affects A too, but yeah, that's what this equation is telling us. And since K is exactly proportional to the rate, if K gets 10 times bigger, my rate is going to be 10 times faster. That's what the rate law up there means. There's a ton of other equations, and those are all integrated rate laws. This is the case where the particular version of each equation that we choose depends on the order. So that's why determining that order x in this case is going to be so important, is because we don't even know which equation we need to use until we know the order x. Now, these integrated rate laws, what they do is they describe how the concentration of our reactant, A is just our generic reactant, in this case that would be concentration of H2O2 for this example, how that depends on time. So A in brackets, that's the concentration of A at some time t, right? Concentrations are always in units of molar. A naught is the concentration of A at time t equals 0. And you can see we have a bunch of different equations that look like that. This one, this one, this one, this one, a bunch of these different equations. Now, the right equation to use, that is something you need to memorize. So the one thing I definitely recommend memorizing is just this sort of order. If the order is 0, that is A versus t is our linear plot. If it's a first order, that's ln of A versus t is the linear plot. And if it's second order, 1 over A versus t is the linear plot. If you memorize that little bit of basically what order, what exponent matches up with which linear plot, so these are the linear plots, right? They're all versus t. Then you know which equation to use. So let's start with 0th order. For 0th order, it's A versus t is the linear plot. So the equations we're looking at are all the equations that have A in them and not any of those other versions of variables. So I'll just use blue arbitrarily. So this one here will work because that's the integrated rate law. Integrated rate laws have A naught. They also, of course, have t. So little t here, I'll get that somewhere in here. Maybe I'll put it up here just because I'm sort of running out of room. So yeah, t is time, and that's always in these equations as well. So it has A naught, the rate constant K, which is in all of these equations, and then small t for time, which is in seconds, but depending on the units of K, we will pick different units of t. So, you know, it could be minutes, years, whatever basically matches the unit on K, because they're going to cancel in the equation. First order then is ln of A. So any of these equations that have ln of A in them are going to be our first order integrated rate laws. So this one up here has ln of A naught, and minus kt. So that's a first order integrated rate law. First order has a bunch of versions actually. This one here is that ratio form, which can be convenient if you're dealing with like percentages. And if you, again, one thing to remember here is like your mathematical rules here. If I want to undo a natural logarithm, the way I do that is I take e to the power of both sides. So that gives me the third form here. If I take e to the power of these, then I will, by multiplying both sides by A naught after I do that, get this final version. So again, just remember that E and ln are sort of inverse operations. If I want to pull something out of an exponential, I need to take ln of both sides to pull stuff out of the exponent. And if I have something in an ln, I need to take e to the power of both sides to get it out. Now, that's first order. For second order, the thing to memorize is 1 over A versus t is linear. So that is our final integrated rate law. Goes to second order. those are always going to be useful if I have, maybe I figure out K, I figure out the order. Now I can go and say how much of my hydrogen peroxide is left at a given time, which is going to be important in a lot of the different problems that we solve. For the last couple equations, those are going to be half-lives. So they're really just another application of integrated rate laws, but just it's often convenient to think about this specific definition of the time it takes to cut the concentration of the reactant in half. So again, A is always your reactant, like H2O2 in this case. Yeah, just a convenient thing to look at. Now, there's nothing really new to memorize here. Just like here, if you've memorized that A goes with 0th order, I can now do that exact same thing for the other ones here. So the 0th order is the half-life that has A in it, or A not in it, but it has to be on top. So this one here works. This is A not on top. That's the 0th order half-life. Similarly, the half-life that has Ln in it will be the 1st order half-life. So that's this one. That one is sort of particularly special because this is the constant half-life. That's particularly useful. It lets you basically just count in units of half-life. It's also basically why this ratio form of the integrated rate law exists, because it doesn't actually matter how much you start with. If I start with from 100% and I want to go down to 50% and then 25% and then 12.5%, like cutting in half and half and half, it always takes sort of the same amount of time to cut in half a certain number of times. It doesn't depend on that initial concentration like it would for the other ones. 2nd order is our last one. That has to be the one that has 1 over A in it. So that's our remaining half-life equation. So you should then be able to, line up when you get the equation sheet. Okay, these equations are the Arrhenius equation. These equations are the integrated rate laws. And then again, for integrated rate laws, you have to be able to match them to the order. So 2nd order with 1 over A in it. 1st order with, 0th order with A, just A in it. And 1st order with ln of A, or again, this other exception here is the e to the power of. You could always use any one of these 3 forms to solve your problem. It's just sort of a matter of saving you a step of algebra. Any 3 of these will work for the 1st order integrated rate law. Once you've picked out the proper equation, these are sort of from the summary slides, right? A lot of times what we do is this infer the parameters from the linear plot. So in this case, this is doing that with the Arrhenius equation. We have rate constant versus t is very nonlinear, but based on having this equation off our equation sheet, if I plot ln of k versus 1 over t, I should get a line that looks like this. Now I do that thing where I match up y equals mx plus b to the equation of the line. I can see that the slope m is negative EA over r. So negative EA over r is equal to negative 7715.7. Now again, one thing you need to know is how to get the unit on the slope. That just comes from the fact that, right, the definition of the slope is that it is, again, like I could actually calculate, it's something you did in middle school or high school or something like that, is you could actually just calculate the slope. I go from a y of 2 to a y of 0, and my x changes from like 0.0033327 to 0.00353 or something like that. And if I just take that delta y and divide it by the delta x, that gives me my slope. Now the delta y over the delta x, again, you don't need to do that because it did that for you when it made the line, but you do need to use that to figure out the unit. So because I'm taking delta y over delta x, I'm taking the y unit over the x unit, which is, again, in this case, ln of anything is unitless, so 1 divided by Kelvin to the minus 1 gives me Kelvin. That's another sort of just fact you need to remember from math, is that 1 over anything to the inverse power, right? Again, remember that Kelvin to the minus 1 means 1 over Kelvin. And so if I take 1 over Kelvin, that flips that back up to just Kelvin on the top. some of the sort of math review there. So this gives us the activation energy. Again, a unit conversion you're responsible for just memorizing is the joules to kilojoules. Again, you can think about it like a kilometer. Kilo means 1,000, so 1,000 joules is 1 kilojoule. So you can either move the decimal place 3 places, 1, 2, 3, or you do a proper stoichiometry step to do that conversion. This exact same approach where we compare to the line works for the integrated rate laws. But note that when we do the integrated rate laws, we do always get the exact same answer out. It's always the case that the K is equal to the absolute value of the slope for all three of these cases. So if you look at your linear plots, you can sort of short circuit it back to, okay, if I look at the slope and I take the absolute value of it, then I get my value of K from that. So I can find the slope, make it positive, and deal with the units properly, and that's going to give me K for whichever version of the integrated rate law, or for whichever plot happens to be the linear one. So this is that summary slide from integrated rate laws. Hopefully a lot of that sort of clears up a little bit about what's going on with all these boxes: integrated rate law, T1/2, the linear plot, right? So this is one of the problems that we did on the quiz, and one of the problems that we do pretty much all the time, right? It's on the review sheet in a couple different places where you look at a bunch of plots and you make all three of these plots, A versus T, ln of A versus T, and 1 over A versus T. A couple of them are going to be pretty weird looking, but one of them should be linear. Whichever one happens to be linear will tell you the order of the reaction. Then it's just a matter of plugging in. Again, you could use the integrated rate law to do a bunch of stuff, find K. Again, remember from the previous slide that in each of these cases, when you do that analysis and compare the equation of the line to the y equals mx plus b, if you take the slope and make it positive, it will end up being the value of the rate constant. The idea here that slope tells you the rate constant also helps you remember the units on K. So K for a zero order reaction, since the linear plot is A versus T, the units on K are, again, the y unit over the x unit. And so that's y unit here is A, so molar per second. Ln of A versus T, right? Ln is unitless, so that's a unit of 1. And then the T is in seconds, so like 1 over seconds, or again, 1 over seconds is the same thing as seconds to the minus first. Then the last one here, if it's 1 over A on the y-axis divided by seconds, you get 1 over molar divided by second, which is this molar to the minus 1, seconds to the minus 1 for the units on K. Now, this does depend, like seconds is our example here, right? A lot of, like on the quiz and the review sheet and stuff like that, sometimes it is like, if time is in minutes, then it would be the y unit over the x unit, so it would just be molar per minute instead of per second, but it always has the same form, molar on the top, and then some time unit on the bottom, seconds, minutes, hours, etc.